Hi everybody, welcome back. Today we're going to work on putting a soft start circuit into this amplifier. And that's what I'm going to call this video, how to install a soft start circuit onto a power supply. Now a little background on what a soft start circuit is. What you see behind you, I have the schematic here, or in front of you I should say, is the schematic of the Marantz 250 amplifier that we're working on currently in our current series here. And these are the filter capacitors that came out of it. The one with the red X on it is a bad capacitor. This one's reading open. This one reads pretty much good. I mean, it's actually in really good condition. But anyway, it's not about that. I want to show you the size of these capacitors. They're huge. They're 20,000 microfarads at 60 volts. And if you look at the amplifier itself, you can see the size of the transformer and how big that is. So you can only imagine what kind of inrush current this circuit is going to draw. Now, for those of you who don't know what I'm talking about, the way a capacitor works is when you first power an amplifier on like this, or any linear power supply like this, and it has very large storage capacitors such as this. A capacitor, when it is fully discharged, when you first present a voltage to it, it will act almost like a short. It will have very, very low impedance, and it is going to cause the transformer to have to deliver an incredible amount of current. And then once the capacitors charge up a little bit, as they charge, the inrush current, that's what that's called, is inrush current. As the capacitors start to charge, that current will begin to drop. Now, that initial shot of current there that we call inrush current can be very significant. For instance, capacitors like this and amplifiers like this and transformers like this, it's not uncommon to see a inrush current just for a split second of over 100 amps. Now you might say, how does that little power cord and how does your 15 amp breaker handle 100 amps or more? Well, breakers and fuses are designed for short-term current spikes like that. So is your transformer. The problem you run into though is if it's too much of an inrush current, like with these great big caps, like it goes on for too long, you could actually pop the circuit breaker in your house. Or you could blow the fuse. Or you can the biggest problem that happens is you can damage the power switch. So this amplifier that we're working on now, the Marantz 250, does not have a power switch. It's designed to be plugged directly into the your preamp, and then you use the power switch of your preamp to switch on the power amp. The problem is that little switch, every time you click it on and off, that inrush current is going to draw a big arc on that switch, and it's going to eventually damage the contacts of the switch. So in order to stop that, what we want to do is, for a short duration of time, we want to limit that inrush current. We want to make it that can only go to a maximum amount, and we want to cut that current down significantly from that 100 amps or so. And by doing that, we're going to save the switch, the power switch on your preamp. We're going to save your breaker in your house from potentially popping, and the fuse from popping, and it will also cause a lot less stress on your power transformer when you first power it up. Now, why they didn't do this on this amplifier, I really don't know. I've done videos on this in the past. All of the Pioneer, the big ones like the SX1050, the SX1250, 1280, 1080, the Marantz 2500 that we did, all those ones that had these massive filter capacitors like this, they all have this circuit called soft start. They call it a soft start because what it does is it lets it softly come up. It charges the capacitors slowly for a little bit, and then once they get built up a little bit, it allows full power to them. And we'll look at how we do that. It's a very simple circuit here in a minute. So again, why this doesn't have it, I don't know. Now, smaller amplifiers that have smaller capacitors, you know, like little caps like this, the inrush current is so fast and so small that it really won't hurt things. But these great big ones can definitely do that. Now, we just compounded the problem on the amplifier we're working on now, because these are 20,000 microfarads. The new ones that I could find that would fit directly in, they're 33,000 microfarads. That's a huge jump. That's a third more capacitance. So the inrush current on this is going to be huge. If we don't do something to tame that, it's not good. The way I've been powering this thing up on the bench is through the dim bulb. And when you turn that on, you'll see these lights get really bright from that inrush current, and the bulb is actually limiting that inrush current. We want to build a circuit that will simulate that. That's what this video is about. Now, looking at the schematic, and I'm just going to hand hold the schematic, you'll just have to live with that. And you can see our power transformer. So here's your mains coming in, P1 and J1. So P1 is your power cord plug that plugs into your mains in your house. J1 is, you have an extra socket here, and you could plug another amplifier or tape deck or something in there and it'll power it. And then it goes directly into the transformer. You can see it goes through a fuse and then straight into the primary of the transformer. Here's the secondary, and this secondary is going to be, the center tap is 0 volts, and each side is going to be about 50 volts AC, RMS, or somewhere around there, I'm not sure. When it's done, it goes through this bridge rectifier and directly into these caps. And you can see it, everything's just a direct wire from the transformer through the bridge and into the caps. And that's where the problem starts, is that these capacitors are going to act like a dead short when you first turn this on. And it's going to cause incredible amounts of current to be drawn here. So what we want to do is we're going to break this line right here, or this line here, I should say. You're in line with the fuse, and we're going to install a low value resistor, like you only need maybe 3 to 5 ohms in there, and it has to be a high wattage resistor. So I have a 50 watt resistor we're going to put in there. And then we want another thing to control that, because once these caps have started to charge and that inrush current has started to drop, we want to take that resistor out of the circuit to allow full power to the amplifier, so you're not drawing current through that resistor all the time and heating it up. And to do that, we're going to use a relay that's going to short out that resistor and just make it look like a straight wire in there again. Now, how do we control the relay? And that's where this is going to be pretty cool. I want the relay to turn on when it senses these capacitors charged past a certain level. And believe it or not, this whole circuit is only going to take 3 components. It's going to take 2 resistors and a relay. I'm going to show you that here in a minute. All right, so here's our schematic, and it's a very simple circuit. As you can see, there's a relay, just a single pole relay, and 2 resistors. Now, this right here goes to the B plus line, and if I get a chance, I'll try to doctor up the Marantz 250 power supply schematic and add this mod in there so you can actually see how it's wired into the power supply. So this goes across the positive B plus rail, and this end of the relay goes to ground. So you basically have your power supply going through this little dropping resistor and through the coil to ground. And what's going to happen is, as the capacitors charge up on your B+, once they charge past a certain point, there will be enough current flowing through here to pull in this relay coil and to close the contacts. And that's going to short out this 4 ohm 50 watt resistor. Now if you look down here, these are your mains. So this would be going to your plug for your mains. You know, this right here. And your hot side, or whatever you want to call it, will go through this resistor and then out to the power transformer. And this one will just go straight through. So you would have, this would be the primary of your power transformer, right? I'm drawing this through the camera viewfinder. Okay, so this would be your transformer, T1 we'll call it. Okay, so all that's going to happen is when we plug this thing in, current's going to flow through this resistor, and it's going to limit the current through this transformer, which is going to limit the current getting into the capacitors. Once the capacitors charge up to a certain rate, it'll build up high enough that this voltage drop and this voltage drop will be enough to bring in this relay, and the relay will click in. It'll bypass this, and then that'll allow the full power potential to the power supply for the amplifier to operate. And the beauty about this is, if for some reason the power supply does not charge up to its nominal level, this is just going to stay in circuit, and which will kind of give you a little bit of current limiting and protect your transformer. So if there's some kind of a short here or something, this is going to get really, really hot, but there's a good chance that at least for a short while, until it can blow the fuse or something, it'll protect your transformer. So this is a great little circuit. And believe it or not, this is not something I invented. If you look at the Pioneer SX1050, SX1250, or many, many other designs, this is essentially how they do it as well. So it's a very similar type of circuit. So again, if I get the chance, I'll put this while I'm talking, I'll put this up on the screen, and you can look at the little modified schematic. If not, we can just we'll see when I actually put it into this amplifier. Now let's show you how I built this thing and what it looks like physically. All right, let me set the camera because it's drifting on me. Here we go. All right, here is the module. You can see how simple it is. These two these blue terminals represent this right here. And this is where we're going to cut this line, L1, and just put the power cord will go into the one terminal, and then out to the transformer goes to the other terminal. And you can see that's paralleled with this large 4 ohm 50 watt resistor, which will actually mount to the chassis on the inside like this. Here's your 5 watt 2K dropping resistor. This has to be a little bit larger sized resistor because because the coil of the relay draws some current, maybe 20 milliamps or so. You're going to need to be able to dissipate that current through this resistor. So at 5 watts, this is not going to get warm at all. You could actually get away. I tested this with a 1 watt or a 2 watt resistor, and it barely got warm. So this is kind of overkill, which is how I want it. Now, we have to determine this value. This is not going to work with every relay. It will work if you buy this relay. So here it is. I'll show you both sides. And flip it, and there's nothing on that side. So this is the relay itself, and you can see it's got 16 amp contacts. And what we need to know is, first of all, this is a 24 volt coil. So the coil needs 24 volts nominally, but you're going to find out that a relay has a pull-in voltage and an operating voltage and a do not exceed voltage. So like on this one, the pull-in voltage is somewhere around 15 to 18 volts is where this is going to pull in. And then it can handle, you can run it continuously between it should run nominally at 24 volts so that it holds the contacts in tight. But it can actually operate up to about 28 volts without really hurting it very much. Now, knowing all that, if we know the current that it operates at, this coil, like I said, under load is going to draw about somewhere around 20 milliamps, 15 to 20, and we know it's 24 volts, you can do Ohm's law and determine the resistance of the DC resistance of the coil. But we could also measure it with a meter, and you'll see it'll be kind of close, but it won't be perfectly perfect. So if we read it, you can see it's about 850 ohms. Okay, so that's what this relay coil is. It's about 850 ohms, and then you can do the math and determine what this has to be, and you'll find out that even at that, you're going to want to change this a little bit, because if you just do the math, so your fully charged voltage on this is going to be somewhere around 57 volts. And so 57 volts minus 24 volts, which is this, that's going to be the voltage drop across the resistor. And if you just calculated based on that, and then you calculated based on the current through the relay, which is somewhere around 15-20 milliamps, you'll come up with a lower value than this. And actually, you have to experiment a little bit, because what you want is, if this exceeds that voltage, you really don't want to exceed that 28 volt maximum for this particular relay. And you can see how this is going to vary from relay to relay. So if I put, I don't know, here's that burned up one from what we were working on. This is also a 24 volt relay, but I can assure you it draws a lot more current than this one. So this resistor would be a very different value from this one. And it would be dissipating a lot more heat, because since this draws a lot more current, because it's probably got a lower resistance. I don't know, I could be wrong. Let's see here. This is the coil on this one. It's got weird pinout. Yeah, you can see this one's only 400 ohms. So you could see. So being 400 instead of 800 ohms, it's going to draw a lot more current. So this resistor will have to deliver a lot more current with the same voltage drop across it, so the wattage will have to be higher. So you see how that all works? And conversely, if I used a relay with a lower current coil on it, I could use a smaller resistor. So you really have to do the math, and you have to do some experimenting to find out what's correct. This one is perfect for what we're doing. Now, the contacts on the output are wired in parallel with this resistor. So you can see this is solid wire here. And that goes up to these two terminals, which are going to wire in series with your mains. So let's just see it work. I'm not going to put the mains into it, but let's see if this thing trips like it's supposed to with the power supply when it's connected to it. Alright, as you can see, we have both our module and a meter wired up to the B+. This is B-, this is B+. Now, you could also wire it across both of them, but you would need even a higher voltage drop resistor and all that. It's not necessary. If this one's charging up, this one is charging up at relatively the same rate. So it's safe to say that unless there's a real serious problem, if this side's charging, so is this one. All right. And if you take a look here, and I know there's always somebody comes on the comments and says, but what if the meteor falls out of the sky and this happens? You know, it's okay, yeah, there's always a scene where you can make a circuit fail, but highly unlikely. All right. So you can see, if I get the probes on here correctly, our 4 ohm resistor is in the circuit right now. So we're pretending that this is going to be your mains line, right? This is the voltage on your B+. I'm going to plug the unit in, and I have the dim bulb connected there so it can charge more slowly so you can actually see this work. If I just plug this directly into the mains without my current limiting bulb, the dim bulb tester, it would all happen so fast you wouldn't really get to see things happen. So here we go. Turning power on. And there you go. When it gets up somewhere in that 35 to 40 volt range, it clicks it on. Now if I shut the power to the amplifier off, and you'll see those bleeder resistors on the capacitors, because there are a set of bleeder resistors, and they're right here and here. They just discharge the capacitors. And you can see when it gets below a certain level, that relay is going to drop out. And you can see the pull-in voltage is way different than the dropout voltage. We're going to get clear down about 5 volts before this thing's going to drop out. There it goes, see? 8 volts, okay? So at 8 volts, it dropped back out. But the pull-in voltage was much higher. And that's how relays work, by the way. Because once that core of that relay is magnetized, it doesn't take very much voltage to hold it. But to first pull it in and overcome the influence of that spring on the actuator, you need a lot more voltage, but you don't need the full 24 volts. It'll come in just before that. So you can see this one came in a little bit below that. Now remember, we were reading the mains voltage. We can also look at the pull-in voltage of the relay, and I can do that by connecting from ground to the output of this resistor right here. Okay, we're now looking across the coil of this relay. Let's turn the power back on. You can see, boom. So you can see it pulled in around 15 to 18 volts, like I said at the beginning of the video. And turning the power off, we'll see how low this gets before it drops. I'm saying about 5 volts. Yeah, it goes even lower than that. Boom, dropped out. So it actually was 3.5 to 4 volts. So it was even lower than I thought. So that just goes to show how these relays work. Now some of you might ask why I do not have a freewheel or flyback diode connected to the coil of this relay. And what I mean by that is normally you'll see a backwards reverse bias diode across this coil, because when this coil drops out, you can actually get a kind of a voltage spike, and it can get really high voltage and it can damage components. Well, we don't need that on this, because you can see there's nothing but a capacitor and a resistor which will absorb any back EMF from this little coil. If this were connected to a transistor or a solid state device that's sensitive to high voltage spikes, you would want that flyback diode on there. But on this one, it's not necessary. You don't need it. You can put one on if you want. It won't hurt anything for good measure, but I'm not going to. That also brings up a comment that somebody gave about this, and that is on the protect circuit for the amplifier, which is this relay right here. Somebody noticed that they did not have a freewheel diode on this one either. But if you notice, there's 2 resistors on here. There's a resistor between here and the transistor. That resistor will absorb a lot of that high voltage spike as this thing's turning off. So I don't really think that this is as susceptible to it. I understand how this goes high impedance when this opens up like this, but really I don't think you're going to have a whole lot of problem with it. I could be wrong, but I think this resistor will kind of protect that from happening. All right, I'm going to install this into the amplifier and then we'll test it out and see how it works. Okay, our little module is installed. You can see it. And I did have to drill a couple little holes back there, and I'll color those screws black like the rest of them. And you can see the little wires going here and here, coming off of that. And then all I did was I just unsoldered the mains lead from the fuse holder, if you can see it way down in there. I'm not sure if you can see it. And then it goes into this side, which goes over to the transformer, and then the other side goes down to the fuse holder then. So we basically just put it right in line with the mains like we said. And right now what I have is I have an AC voltmeter right here connected across that 4 ohm resistor. So we're going to actually see the voltage drop across the 4 ohm resistor. And then you'll see that voltage drop disappear when the relay pulls in. This is monitoring your B+, so you can see it over here. And you can see as the B+ goes up, you'll see at some point in time that that resistor will be shorted out and bypassed. So let's see if we can get the camera there so we don't have any glare. Now I still have the dim bulb tester in so we can see this, but you're going to see it's still going to come up pretty fast. All right, here we go. And that's it. And you can see it drops down. Now I'm going to let this drop out and I'm going to go direct now. We're not going to use the dim bulb, and you're going to see how fast this actually happens. Okay, we no longer have a dim bulb or anything in there. And you're going to see how fast this thing's going to go. I had to put this in manual mode because auto ranging is too slow, and even at that, we'll see what happens. Okay, here we go. You ready? That's it. That fast. And that's how it works. So our little inrush circuit is functional. Well, I hope this was interesting to you. It certainly was a lot of fun for me to make this thing and install it. And now we have an amplifier that we don't have to worry about it trashing the power switch on whatever we plug it into. So that's it for this episode here. In the next one, we're going to troubleshoot this last, the right channel module, and rebuild it just like the other side. And then after that, we'll do another part where we'll actually do some extensive testing of the amplifier. Overwhelmingly, I got comments that you guys want me to do a solder and chat on this one, so we will do that, and should be fun. So until then, I wish you all peace, joy, happiness, and good health in your lives, and stay well and take care. We'll see you again real soon. Bye-bye.